Welcome to a fascinating exploration of one of the most promising yet underreported revolutions in resource extraction. Today, we'll dive into the world of bioleaching, where microscopic bacteria are quietly transforming how we obtain valuable metals while potentially solving critical environmental and resource challenges. As traditional mining continues to scar landscapes and deplete resources, these tiny organisms are showing us a more sustainable path forward, turning what was once waste into treasure through a process that borders on biological alchemy. A microscopic revolution is quietly advancing in the shadow of traditional mining's environmental devastation. Specialized bacteria are being deployed at unprecedented scales to extract valuable metals from previously considered economically unfeasible sources. This process, called bioleaching or biomining, harnesses naturally occurring microorganisms that can oxidize metals and separate them from their surrounding materials. The most recent breakthrough came from researchers at the National University of Singapore, who published findings in March 2023 demonstrating a novel bacterial consortium dominated by Acidithiobacillus ferrooxidans. This remarkable microorganism achieved gold recovery rates exceeding 92% from electronic waste, significantly outperforming conventional chemical leaching methods while using no toxic chemicals. What makes this so revolutionary is that these bacteria essentially digest the metals, converting them into water-soluble, easily collected forms, all through natural biological processes rather than harsh chemical treatments. To understand the significance of this technology, we need to examine the environmental footprint of conventional mining. Traditional operations typically require extensive land disruption, often permanently altering landscapes through open-pit mining and mountaintop removal. These methods consume massive amounts of water. A single gold mine can use billions of gallons annually and generate hazardous waste streams containing cyanide, mercury, and sulfuric acid. The environmental damage extends far beyond the immediate mining zone, causing biodiversity loss, soil erosion, and groundwater contamination that can persist for generations. In stark contrast, bioleaching systems operate in contained environments with minimal chemical inputs, often utilizing waste materials as their primary feedstock. The energy requirements for bioleaching are also substantially lower, with some operations reporting energy savings of up to 40% compared to conventional methods. This dramatic reduction in environmental impact represents a paradigm shift in how we can approach resource extraction, potentially allowing us to meet our technological metal needs without the devastating ecological consequences we've come to associate with mining. The historical trajectory of this technology dates back to the 1950s, when scientists first documented the role of microorganisms in acid mine drainage. What was initially viewed as an environmental problem, bacteria creating acidic conditions that leached metals from mine tailings, has been ingeniously repurposed as a solution. By the 1980s, commercial applications began emerging in copper recovery, but the technology remained limited to low-grade ores and was considered a niche approach. For decades, bioleaching was seen as a curiosity rather than a viable industrial process. However, the past decade has witnessed remarkable advances in genetic engineering, bioreactor design, and process optimization, dramatically expanding potential applications. These technological leaps have transformed bioleaching from an interesting scientific phenomenon to a commercially viable alternative to traditional extraction methods. What was once considered an environmental liability has been reimagined as perhaps one of our most promising tools for sustainable resource recovery, demonstrating how scientific understanding can transform problems into solutions. The primary workhorses in this microbial mining revolution are chemolithotrophic bacteria, remarkable organisms that derive energy from inorganic compounds rather than sunlight or organic carbon. These specialized microbes have evolved extraordinary metabolic pathways that allow them to survive in highly acidic, metal-rich environments that would be lethal to most life forms. Acidithiobacillus ferrooxidans, the most extensively studied bioleaching organism, oxidizes iron and sulfur compounds, effectively dissolving metals from their mineral matrices. What makes these bacteria particularly valuable is their resilience. They thrive in environments with pH levels as low as 1.5 and can withstand metal concentrations that would be toxic to most organisms. Another key player, Leptospirillum ferrooxidans, specializes in iron oxidation and often works synergistically with other microbes in bioleaching communities. Recent metagenomic studies from the Helmholtz Center for Environmental Research identified previously unknown metabolic pathways in these bacterial communities that enable them to process metals more efficiently than scientists had previously understood. These microbial communities represent evolutionary marvels developed over millions of years in extreme environments like volcanic springs, deep-sea hydrothermal vents, and naturally occurring metal-rich soils. The biochemical machinery of these microorganisms is truly remarkable. They possess specialized membrane proteins that pump out toxic metals, enzymes that function at extremely low pH levels that would denature most proteins, and electron transport chains optimized for extracting energy from inorganic substrates. Dr. Barry Johnson at Bangor University made a fascinating discovery that some bioleaching bacteria can form biofilms on mineral surfaces. These biofilms create microenvironments that accelerate metal dissolution through localized electrochemical reactions, essentially creating microscopic extraction factories on the surface of the materials they're processing. This biofilm formation represents a sophisticated biological strategy that dramatically increases the efficiency of metal extraction, creating conditions that maximize the bacteria's ability to separate valuable metals from surrounding materials. The complexity of these natural systems has taken millions of years to evolve, but now we're beginning to understand and harness these mechanisms for our technological needs. Recent advances in synthetic biology have opened new frontiers in this field. Researchers at the Massachusetts Institute of Technology reported in December 2022 that they had successfully engineered strains of Acidithiobacillus with enhanced oxidation capabilities, improving copper recovery rates by 27% compared to wild-type strains. These genetically modified microorganisms represent the first generation of what could become custom-designed microbial mining specialists tailored for specific metals and source materials. By identifying the genetic foundations of metal extraction capabilities and then enhancing these natural abilities, scientists are creating what amount to specialized living tools designed for specific extraction challenges. The implications are profound. We may soon have custom bacterial strains optimized for gold recovery from smartphones, others for extracting rare earth elements from solar panels, and still others designed to process mining waste. This represents a convergence of biotechnology and resource recovery that was unimaginable just a few decades ago, potentially allowing unprecedented precision in metal extraction without the harsh chemicals traditionally required. The timing of these advances couldn't be more critical. The United Nations estimates that global electronic waste reached 54 million metric tons in 2023, with less than 20% properly recycled. This waste contains precious metals in concentrations often exceeding those found in natural ores. A single ton of smartphones contains approximately 350 grams of gold, compared to 5 to 10 grams per ton in a typical gold mine. This means our landfills and storage facilities are effectively becoming some of the richest metal deposits on the planet. Bioleaching offers a sustainable way to tap into this urban mine without the environmental consequences of traditional extraction. The economics are compelling too. Recovering metals from electronic waste using bioleaching can be more cost-effective than mining virgin materials, especially as ore grades decline worldwide and mining operations must go deeper and process more material for the same yield. This convergence of environmental necessity and economic opportunity is driving rapid commercialization of bioleaching technologies specifically targeted at electronic waste processing. Bioleaching operations are now scaling up worldwide. In late 2022, in Finland, Metso Outotec launched the world's largest commercial biomining facility, processing 15,000 tons of electronic waste monthly using proprietary bacterial strains. The facility recovers gold, copper, silver, and rare earth elements at purities exceeding 99%. This isn't just a laboratory curiosity anymore, it's becoming industrial reality. Chinese mining conglomerate China Molybdenum Company announced in January 2023 that it would invest $302 million in bioleaching technologies for its operations in the Democratic Republic of Congo. The company aims to reduce chemical usage by 80% while maintaining production levels. The economic case for biomining has strengthened considerably as metal prices have risen and environmental regulations have tightened. A comprehensive life cycle assessment published in the Journal of Cleaner Production in July 2023 found that bioleaching of electronic waste produces 72% fewer greenhouse gas emissions than primary mining operations for the same quantity of recovered metals. The study also noted significant reductions in acidification potential, water consumption, and ecotoxicity. These economic and environmental advantages are driving major investments in scaling the technology to industrial levels. Beyond electronic waste, researchers are exploring applications for mine tailings. The massive waste piles from conventional mining that often contain residual metals at concentrations too low for traditional recovery methods but potentially viable for biological approaches. The legacy mining district of Rio Tinto in Spain, which has accumulated over 500 million tons of tailings during its 5,000-year mining history, began a pilot bioleaching project in 2023 that aims to extract copper, zinc, and rare earth elements from historical waste deposits while simultaneously reducing acid mine drainage. This represents a remarkable opportunity to address two problems simultaneously: recovering valuable resources while remediating environmental damage from historical mining activities. These waste repositories, once considered permanent environmental liabilities, could be transformed into valuable resources through bioleaching, potentially funding the cleanup of these sites through the metals recovered. This approach could be applied to thousands of abandoned and active mine sites worldwide, turning environmental problems into economic opportunities while reducing the need for new mining operations. The strategic importance of these technologies extends beyond environmental benefits. Nations with limited natural resources but advanced biotechnology capabilities could potentially bypass traditional resource dependencies. With minimal domestic metal reserves but substantial technological infrastructure, Japan has invested heavily in bioleaching research through its metal mining agency. The European Union's Critical Raw Materials Act, finalized in November 2023, explicitly identifies biomining as a priority technology for reducing dependency on imported materials deemed essential for the green energy transition and digital technologies. The legislation allocates €2.1 billion for developing circular economy technologies, with approximately 30% directed toward biological recovery methods. Unlike traditional mining, which requires specific geological formations, bioleaching can be implemented virtually anywhere with appropriate containment facilities. This democratization of resource recovery could significantly alter global supply chains and resource politics in the coming decade as the technology matures from pilot projects to industrial-scale implementation. The potential geopolitical implications are profound. Countries dependent on metal imports could develop domestic, urban mining capabilities based on bioleaching, reducing vulnerability to supply chain disruptions and price volatility. The technology could also empower developing nations to process their electronic waste domestically rather than exporting it to specialized facilities, creating local economic opportunities while reducing the environmental justice concerns associated with waste exports. The convergence of synthetic biology, artificial intelligence, and advanced bioreactor design promises to revolutionize this field further. Researchers at the University of California, Berkeley, are developing programmable metallophores, genetically engineered microorganisms that selectively bind to specific metals with unprecedented precision, potentially allowing for single-step separation of complex metal mixtures. These biological innovations could dramatically simplify metal separation processes that currently require multiple chemical steps, each with its own environmental footprint. Meanwhile, the space mining industry is taking note. NASA's Artemis program includes experiments with bioleaching microorganisms under lunar and Martian conditions, recognizing that biological resource utilization may prove essential for establishing sustainable off-world colonies. Initial results published in Astrobiology in October 2023 suggest that certain extremophile bacteria can function in simulated extraterrestrial regolith, potentially enabling in situ resource utilization for future space missions. The bacteria that evolved in Earth's most extreme environments may help us survive and thrive beyond our planet, extracting essential metals from lunar or Martian soils without the need to transport heavy chemical reagents from Earth. As metal demand continues to surge with the growth of renewable energy infrastructure and digital technologies, these microscopic miners may be humanity's unlikely allies in addressing resource scarcity and environmental sustainability. The bacteria that once thrived in Earth's most inhospitable environments are now poised to help solve some of our most pressing technological and ecological challenges, transforming waste into resources through biological alchemy that would have seemed like science fiction just a generation ago. What makes this approach so promising is its alignment with circular economy principles. Metals recovered through bioleaching can be used in new technologies, which can eventually be processed again using the same biological methods when they reach end of life, creating a sustainable cycle of use and recovery. This contrasts sharply with the linear extract-use-dispose model that has dominated resource utilization since the Industrial Revolution. By harnessing these natural biological processes, we may be able to meet our growing technological metal needs while dramatically reducing the environmental footprint of resource extraction, potentially transforming how we think about resources, waste, and the relationship between technology and the natural world. We've journeyed through the remarkable world of microbial mining, where nature's tiniest organisms are helping solve some of our biggest resource challenges. From the specialized bacteria that thrive in conditions most life forms could never survive, to the sophisticated biofilms they form to extract metals with precision. These microorganisms represent a biological technology millions of years in the making. The applications we've explored, from processing electronic waste and mine tailings to potential extraterrestrial resource extraction, demonstrate how bioleaching is transforming waste into valuable resources while dramatically reducing environmental impact. As this technology scales from laboratories to industrial facilities worldwide, it promises to reshape resource politics, empower nations without traditional mineral deposits, and help create a truly circular economy for metals. The convergence of ancient bacterial adaptations with cutting-edge synthetic biology and artificial intelligence opens possibilities that were unimaginable just years ago. In this microscopic revolution, we find hope that humanity's technological future need not come at the expense of our planet's health, that through biological innovation, we can meet our growing metal needs while healing rather than harming the environment. These bacterial alchemists, turning waste into treasure, may represent one of our most powerful tools for creating a sustainable technological civilization. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.